Hello again everyone, welcome back to ptet.chemistry channel. So this is the first of these series of tutorial MCQs involving group 17 chemistry. So 9.3a is simply my code for group 17 chemistry. Okay, doesn't bother you at all. So we are talking about the standard enthalpy change of formation of HCl and HI. So we are thinking about forming HCl, okay, from let's say H2, which is the element, and Cl2. You gotta form 1 mole of the substance from its elements. Okay, so we need only half and half of it. All the reactants and product in their standard state. A lot of people confuse HCl with hydrochloric acid. Hydrochloric acid is HCl in water. It's called HCl aqueous. This is mixture. It is not a pure substance. This is a pure substance. This is called hydrogen chloride. It is a gas at room temperature and pressure. It's very low boiling point because it's a simple molecular substance. Alright? And it is not ionic, it's got a covalent bond, but that covalent bond can be broken in water because you can hydrolyze it, and you will dissociate into H plus ion, which give you the acid. All right, so don't get confused there. That is probably the first area that a lot of students will get confused in. So in terms of the enthalpy change of formation, so because all of these are in gas, we can do bond energy calculation. You can refer back to my short tutorial video on check out the playlist on chemical energetics, and inside there should be a couple examples on how to use this. Okay, so it's the sum of the bond energy broken minus the sum of the bond energy formed. Okay, so we use that expression. So what are we breaking and what are we forming? It's the same thing for iodine, except that for iodine we are talking about half H2 plus half I2 going to HI, but this is a gas, but iodine is a solid at room temperature and pressure, which means that you have to convert that into a gas first. Okay, so that has no difference at all. Okay, so this one is really no different at all. You just have to convert the solid into the gas, and this is going to be the sublimation. If I just write sub there, refer to the process of converting a solid to a gas. You require breaking the intermolecular forces, okay, to separate them from being a solid to become a gas. It is definitely going to be greater than 0. Alright, and that you can use bond energy. You can use bond energy broken minus the sum of bond energy formed, because now you have gas and gas going to gas. In terms of your Hess cycle, because you're going this way, it does not matter if you're going that way or that way. Your delta HR is simply going to be delta H sublimation of the iodine plus all of that. So bond, I can just copy all of that, can't I? Just copy that. And then I just paste it, and then I just change the color. Nope, I don't want that. I want to change the color to blue. Yeah, okay, so I can afford to do that because, well, you know, I'm on a digital machine, so that one is all possible there. So just like that, okay. So it's slightly different from for HCl. That is for HI. Simply because you need that one additional step to convert the I2 to I2 gas before you can use the bond energy in calculating out or in evaluating the enthalpy change of reaction. So it all really comes down to the bond energy. Alright, so here you are breaking the HH bond and the Cl, and here you are forming the HCl. Okay, here we are talking about breaking the II bond and forming the HI. Of course, there's the HH as well, but then again, what is different and what is the same? Alright, so I'm going to outline what is different and what is the same. So we need to compare Cl and versus maybe if I just write down the 4 bond energy, then you can see what's going on. HCl and HI. So from the periodic table, not from the periodic table, from the data booklet, the Cl give me 244 kilojoule per mole. So these are the bond energy required to break 1 mole of the covalent bond. So I'm not doing calculation in this question. It's a qualitative question where you're just looking at whatever is whatever, yeah? So you need to break that. So you need to break. And then you need to form this. Okay? For Cl, you need to break 244 and then you are forming 431. But for II, you are breaking a weaker bond, but you're not forming such a strong bond. So when you think about it, only C and D could be whatever is accounting for this, yeah? Only C and D is possible. But C and D are quite confusing because they are saying that which one is the most important. Which one is the most important? We involve calculation involving this, and this, right? But which one is going to be more important, all right? So if you work out the difference, okay, if you work out the difference here, 431 minus 299, the difference is 132. The difference is 244 minus 151 is only 93. This is a bigger difference. It is the major factor accounting for the difference in reactivity as well as the enthalpy change for their values to be different. Okay, it has to come down to which one is making a bigger difference. The bigger difference is between the hydrogen halide bond energy, so that is just down to C as the most important factor. Okay, so I've gone through a couple of concepts which is basically revising your chemical energetics. This question, if it is in theory, they could ask you why you can't do it directly. Well, because this is a solid for enthalpy of formation. Can I remind you that there is forming 1 mole of the substance from its element, okay, all in standard state, all right? So that's why you need this extra step, which will be endothermic, okay? Spend enough time on that question already. So next question is asking you which one can readily decompose. So we are looking for HX, okay? Well, not necessarily HX, but H bonded to something. That's why it's called gaseous hydride. So you have HN, you have HCl. I'm just showing the bond, yeah? But obviously this is NH3, this is HCl, this is HI. In steam is H2O, so you're breaking the HO. In terms of the bond that you need to break, I can tell you that this is the weakest covalent bond. So have a look through your data booklet for the values of bond, okay? And then you see that there is the weakest covalent bond. Therefore, it's the one that readily decomposes, easiest to break. And it's a case study under group 17 chemistry that you can get H2 plus I2 when you heat it up. It's also quite a common question in equilibrium involving Kc or Kp because actually it's a reversible reaction. I've just shown it as a full reaction there, okay? So in the next bit of the question, they're asking how does the reducing power of the hydrogen halide increase? Okay, in what order do they increase? When we look at the hydrogen halide, we have X minus 1. So we can think about reducing power of the halide. The I minus is a strong reducing agent. In fact, you learn in O-level, there's only one reducing agent you learn in O-level, which is Ki, whereas you learn KMnO for acidified as your oxidizing agent. You might or might not have learned potassium dichromate 6 as an oxidizing agent as well. So those are the common reducing and oxidizing agent you will have learned in O-level. So Ki is a strong reducing agent, I minus is a strong reducing agent compared to Br minus, compared to I minus, okay? So in terms of reducing power increases, it's going to go from, not I minus, Cl minus. It's going to go from HCl, HBr is stronger, Hi is even stronger reducing agent. So that has to be A there. Okay, so we're talking about reducing power. So number 4 is asking for which one is true for astatine. So astatine is below iodine. So We don't normally deal with astatine chemistry, but what does it tell you? So you know the oxidizing power of the X2. We talk about chlorine. Actually, fluorine is stronger oxidizing agent than chlorine, but your case study typically start from chlorine in A level. So if you have astatine, it should be there, which means that astatine and chloride, okay, what you are saying is this is Cl minus 1 and this is Cl0. Is astatine a good oxidizing agent? Can it oxidize chlorine minus 1 to chlorine 0? The answer is no. It's a weaker oxidizing agent than chlorine. Chlorine can oxidize astatite, which is At minus 1 to At2, but this cannot oxidize Cl minus to Cl0, okay, based on this scale that we know very well. So we also know that corn sulfuric acid, which is a good oxidizing agent, but only if it is concentrated. It lies somewhere in between bromine and chlorine. So it's weaker oxidizing agent than chlorine, but stronger than bromine, stronger than iodine, stronger than astatite therefore, alright? So when you have hot dilute sulfuric acid, only hydrogen astatite, well, that is possible because you need concentrated for it to be a good oxidizing agent. So maybe that is possible, but we'll leave it on the back burner while we'll check through the rest first, okay? So we know that silver iodide is insoluble in even concentrated NH3, but then silver chloride dissolve, which is a white precipitate, dissolve in excess concentrated ammonia, okay? So you gotta have concentrated ammonia. No, actually it dissolves in excess aqueous ammonia as well, okay? Aqueous or concentrated, that will work, but you need a huge excess of it. But the solubility of the silver 1 halide decreases down group 17. So you are not going to dissolve silver astatite just with dilute aqueous ammonia when the silver iodide already doesn't work that way, yeah? Sodium astatite and hot concentrated sulfur acid react to form astatine. So this is talking about there is a redox. Well, when you have astatite, corn sulfur acid is stronger oxidizing agent than this. You can definitely oxidize astatite to astatine, which is astatine 0. So that is definitely true, which means between B and D, I would definitely go for B, because this is not concentrated enough, alright? So this is the last question of this video. So it's giving you a report from a newspaper. So when you spill bromine, you spray water over the scene of the accident, dissolve the bromine and wash it away. What is wrong? What is incorrect? What is wrong? Okay, the spray water that dissolve the bromine. Bromine does not dissolve in water. That is not entirely true. How in the world do you get aqueous bromine? So it's not very soluble. Okay, that's why you get orangey yellow. Okay, instead of the reddish brown color. You see, Br2 liquid versus Br2 aqueous. Br2 liquid is pure, is reddish brown in color. This is not very soluble in water, but it still dissolves a little bit of it. It's orangey yellow. You test for alkene back in O level as well as GCSE. Yeah, bromine does not vaporize readily. It's okay enough, alright. But what is actually wrong is this purple color. Okay, so Br2 gas is actually reddish brown also. Okay, purple gas is I2. I2 gas is purple, but I2 solid is gray solid. So iodine sublime easily, it goes from solid to gas easily. Yeah, okay. So just going straight to the point, bromine is not purple, alright? But bromine is more dense than air. If you compare the molecular mass of bromine, it is so much greater than the molecular mass of nitrogen or the molecular mass of oxygen, both of which make up the majority of air. The composition of air, you learn it in O level or GCSE, yeah? So bromine is a liquid at room temperature and pressure, but it doesn't mean that it has very high boiling point. Yeah, so the boiling point is reasonably low enough for it to vaporize given enough heat. All right, so that's the end of this tutorial video. If you like these videos, please subscribe to the channel, leave a thumbs up, and yeah, let your friends know about the channel. Okay, thank you for watching.